Let us consider this type of test of hypothesis problem. Here we have two samples done from two normal population. Let us assume that the population is normal, distribution of population is normal, and we have two samples, two separate samples. And in this case, let us suppose that these two data represents the survival span of two group of patients with or without effect of a drug. We may represent it as many different ways. This may represent the timing of a athlete in 100-meter sport with or without a drug, with or without a training. We may represent this as the perfection attained by a shooter with or without practice. There may be innumerable ways to represent this data. We assume that in this case the set of data 1 represents the survival span of a group of patient with drugs, and this is without drug. And we should note that one of the data is missing in the second set. In this type of cases, can we say that they have the same mean if it is given that they have same variance? We do not know the variance, but it is given that they have same variance. Then can we test the hypothesis, or can we say that can we infer from this data that these two populations have same mean? In this case this particular type of problem, we should use the t statistics defined by this. This is the t statistics which we should compute first from this data. Here this V is n1 plus n2 minus 2 degrees of the addition of degrees of freedom of both the set of variable. N1 is 10 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9.2, 10, 10.5, 11, 11.8, 12.5, 14, 15, 16, 17. And in 2 the corresponding values are given as 6, 6.5, 7.2, 8, 9, 10, 8.5, 7.5 and 7. So, you can easily calculate x1 bar and x2 bar, s1 square and s2 square in with regard to these two group. X1 bar represents the mean of this, x2 bar this, and s1 square, s2 square correspondingly. It is a very easy task, I am not elaborating on it. I would like to mention that after calculating x1 bar, x2 bar and n1, s1 square, n2, s2 square, n1 and n2 is 10 and 9, and so V, the sum of degrees of freedom of these two sets comes out to be 10 plus 9 minus 2, that is 17. Actually it is 9 plus 8, that is also 17. So, after getting the value of t, if we assume that we are testing at 5% significance level, then we should try to find out from the table that what is the critical region. From the table we see that for n equal to 17 degrees of freedom, V equal to 17, sorry, for 17 degrees of freedom, the t distribution table shows that the value of probability of t greater than 2.110 is actually 0.025. This can be easily found out. This is the t distribution table, and if we find out the value of n here and pass on to find out the value of 0.025 here. So, these two row and column meets at 2.110. So, this is the value of the probability of the critical region. So, what is the critical region? The critical region will be at 5% significance level minus 2.110 minus infinity union 2.110 plus infinity. This is the critical region. So, we can easily infer after calculating the value of t, we should first calculate the value of t from this table here, and then since the critical region is given in this way, we should find whether this t lies within the critical region, and depending on that, if the computed value of t lies within the critical region at 5% level of significance, we reject H naught, otherwise we accept H naught. In this case, I suppose you should find it out that the value of t will not lie in the critical region and we may accept the null hypothesis. So, I hope you will be able to test this hypothesis. And then if we assume this hypothesis that they have the same mean, given that they have the same variance, we can test this hypothesis at a given significance level also. So, we first assumed that the population which has same standard deviation has the same mean also. This hypothesis can be tested. For that, we will have to use F statistics, which F statistics is given by S1 square by S2 square. That is another story, and we can test this hypothesis that they have the same mean given that they have same standard deviation.